Many of the tools and techniques common in open-hole fishing cannot be used in cased-hole operations due to the restrictive nature of the casing. Sidetracking, for example, an easy option in open hole, was not widely used in cased hole situations until recently. The most common cased hole fishing projects involve removal of stuck production strings. Stuck production tubing can result from collapsed casing that wedges tubing, or tubing and casing leaks that allow sand and other debris to enter the casing annulus. Dehydrated mud in the casing annulus can also stick the string. With stuck pipe or tubing, the first step is to determine the free point or stuck point of the fish. Using a free point indicator run on wire line, the stuck point can be determined and the free tubing removed to this point. In single completions with one string of production tubing in the casing, sanded up or mud-stuck tubing can be freed by a conventional washover operation. A shoe run on wash pipe is lowered over the fish and sand or mud is circulated back to the surface for removal from the wellbore. Unlike shoes used in open hole operations, cased hole washover shoes have smooth exteriors to prevent damage to the casing. Next, a trip is made with an overshot and jarring assembly to engage the fish. When the washover has freed all of the remaining fish, it is pulled from the hole. If only part of the fish is free following washover, the freed portion is cut or backed off and pulled so another washover can begin. If the inside of the fish is plugged, preventing entry of wireline tools, the tubing can be recovered with an outside cutter. Following washover, the shoe is removed and replaced by an outside cutter on the bottom of the washover string. The cutter is run over the top of the fish to the desired depth, and the tubing is mechanically cut by rotating the string. The cutter then acts as a retriever, and the plugged tubing can now be brought to the surface inside the wash pipe. Removal of permanent packers from the well also calls for unique fishing tools and techniques. Several different types of packer retrievers are used, depending on packer type and packer accessories used during completion. A proven method to retrieve a permanent packer in one trip enlists the use of a packer retriever assembly. Its custom-made tungsten carbide-faced shoe is dressed to near casing ID, so it cuts only the slip section of the packer. Padding above the shoe prevents damage to the casing wall. The retrieving assembly, with a correctly selected grapple for the packer bore, is run below hydraulic jars, collars, and a boot basket, which collects metal debris cut loose by the shoe. The spear and extension in the assembly is lowered through the packer. Milling over proceeds until the packer is milled free. The spear engages the packer body and it is removed from the well. This standard method of packer retrieval works only if there is no tailpipe below the packer or if a mill-out extension has been installed when the packer was run in the hole. If sealed bore extensions are located below the packer without a mill-out extension, another type of packer retriever assembly is run for one-trip recovery. It incorporates a top bushing that crosses over from a boot basket to the wash pipe extension, a J-latch assembly with wash pipe connections at the top and bottom, and a burning shoe. Connected to the inside of the J-latch assembly is a mandrel, spear extension, spear stop sub, and spear. The assembly is lowered into the well until the spear stabs into the packer mandrel. A gentle pull on the spear confirms that the packer is engaged. J-latches are released, the shoe is lowered, and rotation begins to mill over the packer. With the packer milled free, the string is picked up until the J-latches are secured into the assembly, and the packer, engaged by the spear, is removed from the well. Multiple completions where more than one string of tubing is placed side by side in the casing present another challenge. Washover is not an option here because of the limited space in the casing. Instead, the well operator will use a specialized wash-down mill run on the end of a small tubing string. Debris is washed from the casing annulus and circulated from the well. In sandy environments, a gravel pack assembly may be located below the packer. Its removal is accomplished using conventional washover, milling, and retrieval tools. However, when rapid sand backfilling is likely, and where the gravel pack assembly may become restuck while tripping the pipe for an overshot, a trip saver tool is recommended. The trip saver is run in place of the top bushing of the wash pipe. It provides a mandrel on which an overshot can be placed inside the wash pipe. After washover is completed, the well is circulated clean. The mandrel with the overshot is released from the wash pipe top and lowered until the overshot latches to the gravel pack assembly, ensuring efficient one-trip retrieval. Another major area requiring cased hole fishing focuses on casing problems themselves. When leaks are located in free pipe above the cemented level of the casing is cut or backed off below the problem area and replaced with new pipe. If the casing was backed off, the new casing is run back in the well and the string is screwed back together. If the casing was cut, it is dressed off to remove burrs. An external casing patch is then screwed onto a string of new casing and run in the hole. The patch is engaged onto the old casing in a manner similar to an overshot, and a gentle upward pull collapses the seal assembly made of lead or rubber around the casing. The entire string is pressure tested to ensure a good seal. When casing leaks are located below the cemented level, making them inaccessible to retrieve and repair, and all other repair attempts have failed, such as squeeze cementing, Homco internal casing patches are recommended. Originally designed to seal unwanted perforations, they have proven to be very effective in sealing most types of casing leaks. The Homco internal casing patch is made of corrugated steel covered with a fiberglass mat and coated with an epoxy resin prior to running. The patch is positioned over the leak area and is set by hydraulically pulling a collet expander through the corrugated patch, flattening it against the casing wall. The resin extrudes in and around the fiberglass mat, serving as a secondary sealing agent. The setting tool is then retrieved while the epoxy sets. The standard Homco steel liner patch has a 1/8 inch steel wall thickness, leaving a total casing ID reduction of 3/8 of an inch. In special situations where higher pressure is a concern, a heavier 3/16 inch patch is available. Also supplies lead-wrapped patches for high-temperature situations. If the weather operator finds the casing problem is more severe, such as collapsed or parted casing, more aggressive measures must be undertaken. With slightly collapsed casing, the common tool used is a casing roller. In this procedure, a set of hydraulic jars, bumper jars, and drill collars are run above the roller. When the desired depth is reached, right-hand rotation and the eccentric action of the roller will return the casing to its original shape and ID. More severely collapsed casing can be repaired with a casing swedge. A bumper jar, hydraulic jar, and drill collars are located above the swedge. The swedge is driven through the damaged section by hitting down with the bumper jar and drill collars, opening the casing to its original shape and ID. The hydraulic jar allows the swedge to be retrieved if it becomes stuck during this procedure. When the problem is parted casing, bringing the two sections into correct alignment requires still other, more specialized weather remedial tools. The most effective of these is a guide assembly and watermelon mill called a lace joint. The lace joint is lowered on drill collars into the bottom casing, and the milling section is worked back and forth through the parted area until the separated casings are realigned. To cement the joined sections together, the operator uses a casing alignment tool. The OD of this tool is built to drift the ID of the casing, and it is run below a cement retainer. The casing alignment tool is placed across the separated casing and the retainer is set. Cement is pumped through the casing alignment tool, through the casing wall, and into the formation, sealing the casing joint 360 degrees around the external casing wall. After the cement sets, the cement retainer and alignment tool are completely drilled out, achieving proper ID size and integrity. When all casing repair methods fail, it becomes necessary to sidetrack if the well is to be saved. Although a sidetrack can be accomplished by cutting or milling a section through the casing and then drilling out using a directional assembly, using a whipstock to mill a window is usually the most effective and least costly procedure to establish a sidetrack. Weatherford's Whipback is one of the most popular whipstocks in use today. The Whipback is a bottom trip whipstock which can function as a permanent whipstock or can be removed after the sidetracked hole has been drilled. A solid bottom is required to set the whipstock. A bridge plug is frequently used for this purpose. The bridge plug should be set approximately 5 feet above a casing collar. This will allow the window to be milled through the tube portion of the casing, avoiding the thicker coupling area. The whipstock is connected to a starter mill with a shear bolt and lowered into the well on the work string. One joint of drill pipe and a mule shoe sub, if the face of the whipstock has to be oriented, are placed above the starter mill and below the drill collars. If this is a blind sidetrack and the whipstock face or concave does not have to be oriented in a particular direction, the whipstock is lowered until the bottom trip assembly of the whipback rests on the bridge plug. 2,000 to 4,000 pounds of weight are applied to the whipback, shearing the bottom trip assembly and setting the whipstock. Additional weight is slacked off until the shear bolt attaching the starter mill to the whipstock shears. The whipstock is now set and milling can begin. If the concave has to be oriented in a particular direction, the assembly is lowered to approximately 20 feet above the bridge plug. At this point, a wire line with a gyro is run in the work string until the mule shoe sub has been reached. Readings are taken to determine which way the concave is facing. After setting the whipback, rotation and circulation are established. The string is slowly lowered until there is an indication that the starter mill has reached the top of the area to be milled. Pipe should be marked at this time and milling continued until about 24 inches have been made. All cuttings are circulated out and the work string is pulled out. The starter mill and mule shoe sub are replaced by a window mill and rough OD watermelon mill. This assembly is tripped in the hole to approximately 5 feet above the whipback. Circulation and rotation are re-established. The window milling assembly is lowered until the 24-inch section previously milled is reached. Milling proceeds until the window is completed and the milling assembly has penetrated 4 to 6 feet of open hole. After the window is established, milling continues back and forth through the window area until the assembly can do so without any torque or drag. In medium radius horizontal wells, it is sometimes a good idea to make one additional mill run if a long horizontal area is to be drilled. This run will lengthen the window, making it easier for the drilling assembly to pass through the window when horizontal reach is long and drag becomes severe. Once the new radius or sidetrack is complete, the whipback can be recovered using a special retrieval hook or a threaded die collar. This is particularly useful in producing wells where multilateral bores are added to an existing productive interval. Era offers a complete line of whipstocks. In addition to the popular whipback, Packer type, hinged and open hole whipstocks are also available. Weatherford employs the industry's widest range of milling tools. Among the most common are junk mills, used to mill packers, bridge plugs, cement, perforating guns, drill pipe, tool joints, and other obstructions. Junk mills can incorporate a concave, convex, or flat bottom, depending on the application. Other mills include the cone buster, used for milling up rock bit cones. The taper mill, used to dress liner tops and clean out tight spots in casings. And the pilot mill, designed to mill casing, liners, rotary shoes, and large ID tubing. Additionally, weather systems now feature advanced quick-cut technology. This alternative incorporates innovative square-cut tungsten carbide inserts, which improve chip control and maximize casing penetration. The advantages are faster, more efficient milling performance,